The next topic of chapter 6 is how to work with sums of independent random variables. We're going to first look at, for a sum of two continuous random variables, how we're going to work with it. If you have x and y, they have a joint density fx. Then if you're curious about the sum of x and y, so we write x and y, and as you can see that immediately we change the subscript of the PDF function f with x plus y to indicate that we're looking at this sum of the two random variables. We use a dummy variable z here. So if you want to work with the sum of the two continuous random variables and you have the joint of fx y, it is equivalent to say that, well, I can integrate with respect to x of the joint density if I can replace my x with y, y with x. Okay, so that's why you have this one way. Or if I want to focus on y, then I still have my joint fxy, but then I replace my x with y and then integrate out y. One way to think about this is because, well, if you're looking at the sum of the two, it's going to still be one random variable. But what you have is the joint of x and y. So we know that we should do y integration to get like one of the two when we're doing marginal. But right now we're looking at the sum of the two. So you simply replace the expression of one of them, say y in terms of x, or x in terms of y, and then integrate out that random variable, you will get the joint. You will get the sum of the two. So when you have a special case of x and y being independent, then you can use what we call the convolution formula. So it's very similar to what we had before in some sense, but then we're replacing the joint with the product of the marginal, okay, because they are independent, as we covered before. And we call this the CDF f x plus y is the convolution of the distributions of the CDF of x and CDF of y. So notice how these two are linked. Okay, we simply replace the joint with the product of the marginal because we have independence.